town of Gatesville is adding an activated sludge system to its water treatment plant to meet a water quality standard of 30 milligrams per liter of BOD5 and 30 milligrams per liter of suspended solids. Assuming the BOD5 of the suspended solids may be estimated as 63% of the suspended solids concentration and a microbial concentration of 2,000 milligrams per liter in the CMFR, estimate the required volume of the CMFR for a flow rate of 0.15 meters cubed per second, an inlet BOD concentration of 84 milligrams per liter, Ks equals to 100 milligrams per liter, mu max is equal to 2.5 inverse days, Kd is equal to 0.05 inverse days, and Y is equal to 0.5 milligrams of biomass per milligrams of BOD5. Okay, right away when we see this required volume phrase, typically that almost always means that our second to last step is setting the mean residence time equal to volume over flow rate. And then if we know the mean residence time and we know the flow rate, we can rearrange this to solve for V, the volume. So we know this is going to be our second to last step. Now we're given some information about what S has to be, and we know what X is. So if we go back to our expressions for the soluble BOD concentration and the biomass concentration, we can see that both theta C, the cell mean residence time, and theta show up in these expressions. Now remember, we're trying to get to this theta, and we know X and we know S, but we don't know theta C. So if we just look at our expression for X, we have one equation with two unknowns, theta C and theta. But if we go back to our expression for S, we know S, so the only unknown we have here is theta C. So what we're going to do is first solve our S expression for theta C, and then we're going to solve our X expression for, that is not how you spell expression for theta, and then we're going to use this theta equals volume over flow rate to solve for this volume. That's still not how you spell expression, is it? Whatever, that's not the point of the problem. You all get what I'm saying. I'm going to keep moving. Okay. So before we get into all that, the first thing we need to know is that the total water quality standard that we need to meet is 30 milligrams per liter of BOD5. That means that our soluble BOD concentration has to be the total allowed minus the amount in suspended solids. Okay? So that is 30 milligrams per liter allowed minus 63% of the suspended solids is BOD5, and we have 30 milligrams of suspended solids, so we'll have 0.63 times 30 milligrams per liter, and that's going to give us a soluble BOD concentration of 11.1 milligrams per liter. Okay, so this is the amount of soluble BOD that has to leave our sludge or activated sludge system in order to maintain this allowable concentration of 30 milligrams per liter. So over here, I'm just going to write down this result so I can erase this and make some room. Okay, so now we can get to S is equal to Ks times 1 plus Kd theta C all over theta C times mu max minus Kd and minus 1. Okay, solving for theta C, so I'm just going to rearrange by multiplying both sides by the denominator. So I'll have S theta C times mu max minus Kd minus S is equal to Ks times 1 plus Kd theta C. Okay, and now what I want to do is get all these theta C terms on one side so I can rearrange. I'll have theta C times S mu max minus S Kd, so that's just distributing this S to both of these terms. And then I'm going to take minus Ks Kd over from this side. And then all of that is going to be equal to Ks plus S. Therefore, theta C is equal to S mu max minus SKD minus KSKD in the denominator, and KS plus S in the numerator. Okay, this half saturation constant is 100 milligrams per liter. S is this 11.1 milligrams per liter. Mu max is 2.5 inverse days. KD is 0.05 inverse days. So plugging all that in, we get a cell mean residence time approximately equal to 5 days. Okay, so I'm just going to write that over here and erase to make room. All right, now we can go to our expression for the biomass. So X is equal to theta C times Y times S naught minus S all over theta times 1 plus KD theta C. Okay, this one's much easier to rearrange. All we do is multiply both sides by theta and divide both sides by X. And we get theta is equal to theta cy times S naught minus S over X times 1 plus KD theta C. Okay, this theta C is what we just solved for. This is 5 days. Y is 0.5 milligrams X per milligrams BOD5. S naught is this 84 milligrams per liter. S is the 11.1 milligrams per liter. X is this 2,000 milligrams per liter here. KD is 0.05 inverse days, and we're good to go. So plugging all this in, we get a mean residence time equal to 0.073 days, which, just to point out, is much less than our cell mean residence time. Why is that? Because these cells are getting recycled. These cells are getting recycled. Okay, so even though a particle might only spend 0.073 days in the CMFR the first go around, these cells are going back into the CMFR multiple times as they get recycled. So they spend a lot longer in the CMFR, or in the system. Okay, so now we have this mean residence time is 0.073 days. And all that's left to do is rearrange this expression. Probably don't have to erase, but I will. But we have the required volume is equal to theta Q. Okay, this theta is what we just solved for, 0.073 days. This Q is the 0.15 meters cubed per second. So we'll have to get these days into seconds or vice versa. And if you do that, what you should get is a final volume equal to 970 meters cubed. All right, looks scary, kind of sounds scary at the beginning, but overall what it comes down to is just a bit of algebra.